Kia ora Year 12. This is a really short iterative methods question for George, and it's mainly to give you the idea that there are often two parts to problems about iterative methods. The first part is one where we're given a formula that lets us update our value of x. And the idea of convergence is that the updating that we do from value x0 to x1 to x2 converges. In other words, we end up at a particular value of x, and in this case we're calling that alpha. So we're going to take this updating formula and see what happens when we start with an initial value of 2. And we have to give the result of each iteration to 6 decimal places, and our final answer for alpha has to be correct to 4. Right? As you know, I find these some of the most boring questions in the maths universe, except that there's something kind of cool about seeing it converge. So let's look at the formula we've got here. In the first part of the question, all we have to do is to use this updating method, and we're looking for the value of x to get closer and closer to the last value of x, and when it's not moving out to 4 decimal places, we say that it's converged. We're given a starting value of 2, so I'm going to show you the working for the first one of these, and from there I think it's fine just to chuck it into your calculator. So we take that value of 2 and we go 2 times 2 to the power of 6 plus 12 times 2 over 3 times 2 to the power of 5 plus 8. And that gives us 1.461538. And that's going to 6 dp. Now I use that as my new value to put in to my updater. So we take this number and we put it in here, and we get out 1.322263. And we keep on going until those values are converging. Now there are some situations where they won't converge, and we looked at those in class ages ago, and it comes down to the slope of the function around where I'm working. But in this case it updates and it converges really, really quickly. So going out to 6 decimal places, we get some pretty speedy convergence here. Now I'm saying that this is converged because when I look out to 4 dp, I can see that it's not changing. So that tells me that alpha, correct to 4 decimal places, is 1.3195 to 4 dp. Let's look at the second part of the question. Well, we have to state an equation satisfied by alpha, and hence find the exact value of alpha. So alpha is the value where we've got convergence, and convergence means that x1 is roughly the same as xn plus 1, and we call that alpha. Okay, so that's my definition of convergence. So to figure out the exact value for where that happens, I'm going to get rid of all of this horrible approximate mess. And instead of working with xn and xn plus 1, I'm going to say that when they've converged, what am I going to say? Not when they have converged. I'm just going to state the equation using alpha. So I'm going to say let alpha equal x. So now I've got x is equal to 2x to the power of 6 plus 12x over 3x to the power of, oops, I don't know what's happened there, just get rid of that, 3x to the power of 5 plus 8. Now what I want to do is to solve this equation for x. So we can multiply both sides by the denominator and then solve. So this is an example where we can get an exact value. So we have 3x to the power of 6 plus 8x is equal to 2x to the power of 6 plus 12x. Let's bring everything over to one side. We have x to the power of 6 minus 4x is equal to 0. And we can solve this by factorizing. So we have x times x to the power of 5 minus 4 equals 0. So either x equals 0 or x to the power of 5 is equal to 4. So x is equal to the 5th root of 4. Now just notice as an aside, I'm working in real solutions territory here. Obviously there are 5 solutions to that equation, and it's a nice bit of complex numbers revision to find those other 4 solutions, right? Because we know that they're evenly spaced around the unit circle. But that wasn't at all what was intended by this little question on iterative methods. And so what we've got is that the exact value of alpha is this one here, the 5th root of 4. Okay, but you might want to do this one for a bit of merit level practice. We could let z equal r cis theta, and then we'd have z to the power of 5 is equal to 4 cis 0 plus 2 n pi, and so on. Okay, but what we're looking for here was nothing to do with that. It was just to state an equation satisfied by alpha and find the exact value of alpha. So George, I hope that made things better and not worse. Let me know if it did. I'm going to do a harder iterative methods problem tonight or tomorrow night, and it's one that uses a whole lot of geometry. So I'll just give you a quick preview of that one now. This question from June 2018 is pretty cool. First you have to solve a geometric problem and show that we've got this relationship, and this is one where it's pretty obvious why we have to do iterative methods, because there's no nice analytical solution for theta in there. Okay, so thanks for watching, and just keep on emailing in with questions that you'd like me to video, and I'll slowly get around to doing them.